different crystal habits, rods, needles, plates, and so on. Any crystalline compound can do that, depending on the crystallization conditions. Polymorphism infers different shapes, but also different internal structures. Each polymorph will have a different internal arrangement of atoms, corresponding to different free energies. These structures are generally determined by X-ray diffraction. Here we have the structure of graphite, the stable hexagonal polymorphic form of carbon. And here, the structure of its polymorphic form, the diamond. Few polymorphs are as different as graphite and diamond, but polymorphic forms do always differ in their physical properties. Probably all compounds, organic and inorganic, show polymorphism. Many are quite familiar. Quartz, cristobalite, calcite, aragonite, rutile, anatase, alpha and beta brass, orthorhombic and monoclinic sulfur. That polymorphs differ in shape is shown by DDT. This is the unstable form 2 crystallized from a supercooled melt on a microscope slide. The stable form 1 crystallizes from the same melt as spherulites. Here we see both forms. At room temperature they will continue to grow until all of the melt has crystallized. Then the stable spherulitic form 1 will proceed to grow through the unstable form 2, a solid-solid polymorphic transformation. Because polymorphs differ internally, they also show different physical properties. Electrical properties such as conductivity and capacitance, mechanical properties such as hardness and elasticity, optical properties such as color and refractive indices, and thermal properties such as melting point and transition temperatures. The properties most useful to those of us who wish to produce and study polymorphic forms are the usual properties we used to use to characterize and identify compounds before FTIR, mass spec, NMR, and such. I still use density, melting points, and so on, but I also still use the polarized light microscope, PLM. I use PLM because I can see directly what is happening. No digital readout or chart recording. One has to try to interpret in terms of just what happened. Instead, you see the crystals of each polymorph individually. You can quickly detect impurities, determine relative stability, prepare unstable forms, and observe transitions, all on a microscope slide. To better understand polymorphism, we need to understand one-component phase diagrams, the old triple point, PT diagram. Each polymorph has its own PT diagram, although all polymorphs of a given compound have the same liquid and vapor phases, hence the boiling point curve is common to both polymorph PT diagrams. Two polymorphs of a given compound will have each its own sublimation curve, here shown as Roman 2 vapor and Roman 1 vapor. If we specify as one possibility that the boiling point curve, LV, intersects the sublimation curves above the transition temperature, we have this beginning of an enantiotropic phase diagram for polymorphs. Enantiotropic systems are reversible in that the transition temperature lies below the melting points of the two forms. We would derive the monotropic system phase diagram by having the boiling point curve intersect the sublimation curves below the transition temperature. As we have it here for the enantiotropic reversible system, the pressure function of the transition temperature and the melting points will be shown in the next diagram. Here we have the full diagram for the reversible enantiotopic system. Roman 1, Roman 2 curve on the upper left is the transition temperature as it changes with pressure. The melting points, 1L and Roman 2L, are shown at higher temperatures. We would normally be working with a section of this diagram where atmospheric pressure in a horizontal line, which then as you heat along that line would first show the transition temperature and then the two melting points. At this point, I want to show how polymorphs behave microscopically. We can begin with the preparation of unstable polymorphs. Unstable polymorphs always have higher vapor pressures and higher solubilities, but lower melting points. To prepare unstable polymorphs, the key is supersaturation of the vapor or solution. This is usually done by supercooling, and this applies to the supercooling of the melt as well. Let me show you first my hot stage. It is an ordinary microscope slide, but coated with a conductive coating so that I can heat it electrically to temperatures up to 300 or 400 degrees. I put a sublimation cell here now. It's a 1 centimeter length of ordinary glass tubing, and here a milligram or less of picramic acid in the bottom of the cell. And if we then focus on a cover slip, which will be placed on the top of this cell to enclose the whole system, we can watch the sublimation of picramic acid. Here the nuclei of the stable phase are beginning to appear, and we'll skip a little bit of time. And you can perhaps already see clear areas around the slowly growing stable crystals. The rest of the slide and the areas around those stable crystals are now covered with a very thin film of the unstable polymorphic form. And here, skipping a little more time, you can see that the stable polymorphic form has grown quite considerably at the expense of the unstable polymorph, which of course has a higher vapor pressure. We can place a slide preparation or crystals between two cover slips on top of this electrically coated slide, and then observe it as heated or cooled. And in this situation shown here, we're watching the spontaneous cooling of benzo triazole. The hot stage itself is just acting as a support for the moment and is at room temperature. This is the stable polymorphic form of benzotriazole, which will very soon now show crystallization of the unstable form, which is here. The stable form continues to grow through this unstable crystal growth. The unstable form continues to grow on through the melt. There is a third polymorphic form, which we might go look for. These are little, more or less diamond-shaped crystals. Note here the crystal quake on the left. This is a result of strain in the growing crystals and causes some interesting effects, one of which we will look at a little bit later. This is a nucleation of a spherulite of the form 2, metastable form, and it is surrounding the form 3, the most unstable form, and the crystal fronts of the form 2 are meeting. Here we have the pseudomorph of the, showing the transformation of 1 through form 2. So it's a form 1 pseudomorph of 2. Darker because of the light scattering by breaking up the crystals as a result of their different densities. You can see the transformation proceeding in the lower left. This is a pretty quick way to determine whether polymorphs exist, and right now I'm trying to determine whether it's reversible or not. And this is done with a hot needle, heated with an alcohol lamp. And if I place it on here, you'll notice as soon as it comes in that the stable form grows. The transformation does not reverse, it simply speeds up the transformation. We can show a reversible transformation by the same means, a hot needle, with mercuric iodide. This is the low temperature red form of mercuric iodide. A hot needle placed on this surface will conduct enough heat through the cover slip to raise the temperature above 130 degrees, the transition temperature, and transform the red form to the high temperature yellow form. So here we do reverse the transition with heat. And of course it cools back down very quickly to give the stable form again, the red. I have now moved the EC coated slide about a centimeter toward me so that I can slip the preparation of ammonium nitrate here under the hot edge, which is off camera at the bottom. And I can now heat to show a temperature gradient between the different portions of the field. At the bottom it will be hotter, at the top it will be cool. The ammonium nitrate has a high temperature polymorphic form, cubic, and it is the darker portion of the field, and this is now cooling, and the form 4 is beginning to grow down through it as the preparation cools. If I warm up the EC slide a little bit, I can stop the growth of form 4 and warm it up enough so that it even reverses just a little bit. And then we can resume the cooling. And ammonium nitrate has 5 different polymorphic forms that we know of. Probably has more. The number of polymorphs you have depends on how hard you look for them. One of those forms is below room temperature, so we won't see that. If we look at this field, however, as it continues to cool, we should see the crystals of form 3 or maybe 2. We never know which one is going to nucleate until we see it. There's about an even chance of one or the other. But we should see that one of the two beginning to grow in the upper right, I believe. It also supercools easily, and perhaps that's what determines which of those two forms actually does appear. When it does appear, you'll notice a strange difference in growth rate in different portions of the system. It's already begun now in the upper right. It's a little bit subtle because the polarization colors are not too different, but you can see it sneaking down the right side, and it'll soon take off and actually grow down around the bottom and come back up on the left side. Here's where it begins to spurt ahead, and off camera it's it's bridged across one of the grain boundaries and surging ahead and sort of cutting off the advance of the same form, actually, but different crystals of it. Transformation then to form, this turns out to be form 2, the room temperature stable form, so there will not be, in this case, another transformation. We could reheat this with the EC coated slide just off camera outside and reverse those transitions. All of them are reversible, and we can calibrate this slide so that we can put an eyepiece micrometer in the microscope, superpose it on the field of view, and calibrate it so that we can determine more accurately the transition temperatures. Here comes form 4 growing back up through form 3. We've heated it, in other words, and we must have heated it above about 82 degrees in order to cause this form to advance into the more stable low temperature form. The advancing crystal front is fairly linear and would be more so if we were doing this more slowly. And you can measure these transition temperatures with this simple EC coated slide to plus or minus 1 degree. This is the transition of forms 4 to 5, and as we mentioned before, form 5 is cubic, and the temperature of this transition is about 132 degrees. You can be sure that the darker phase at the bottom, form 5, is really crystalline because those air bubbles would otherwise be moving around a little bit, and they seem to be pretty solid. Here, just for a moment, we cooled it back down and reversed the transition, and now resuming the heating, we can drive this transition zone between ammonium nitrate forms 4 and 5 up into the upper part of the field. This slide is very useful for this purpose in order to very quickly determine whether you do have polymorphs, and then to characterize it in terms of reversibility or non-reversibility, and measuring the transition temperatures. It's a successor to the old hot wire stage that Francis Jones and Norman Hartshorne have used. This is sulfur. You can't have a tape on polymorphism without mentioning monoclinic and orthorhombic sulfur. These are crystals of sulfur. Most of them are orthorhombic. Here they're nucleating droplets as they grow this is a solution of sulfur and aniline. As it cools down, you can see a solution phase transformation, so to speak, of the droplets over to the crystals. Here we have some monoclinic blades, the colorful ones, and orthorhombic crystals, the darker ones. The orthorhombic ones are more stable, and there's a slow transformation in aniline solution at room temperature, but the bladed crystals should slowly disappear. We'll skip some time here, and you can see that the blades have shortened a little bit, particularly the one left of center. We'll skip a couple more intervals of time. Actually, the time that we're skipping here is the order of half an hour. So this is time-lapse, so to speak, over about a 2-hour period, showing the change of monoclinic sulfur, the unstable form, to the stable form. We've had a vapor phase transformation with picramic acid already. We've had the solid phase transformations with benzo triazole and ammonium nitrate, and now this is a solution phase transformation for monoclinic to orthorhombic sulfur. I think this time we might have one more, and we'll skip a little bit more time. There's been quite a change in the 2 hours that this has taken place, but obviously it's going to be another 2 hours before all of the monoclinic form has disappeared. Next, I want to show you a very unusual set of transformations involving liquid crystals. This is disodium chromoglycate, Intol, a drug. And this is cooling spontaneously on the EC-coated slide, and this is a middle phase, or mesophase actually, an unstable polymorphic form in the liquid crystalline form of Intol. Here it changed on further cooling to the pneumatic phase, and it's crystallizing out of the aqueous solution. Actually, there are three polymorphs. The pneumatic, a smectic phase, which with lyotropic mesophases is usually called a middle phase, an analogy with the soaps, and then a high temperature solid phase. So if we do this again, we will go to a little bit higher temperature. We have to be above about 73 degrees in order to see the solid phase. And here we see the solid crystals. They immediately change at 73 degrees to our can of worms, I like to call it, which is the lyotropic middle mesophase. This has more structure, obviously, than the pneumatic phase. And this is cooling spontaneously now, and it's about to collapse to show the pneumatic structure. Here it goes. Now, an interesting point with these mesophases is that they have several hundred molecules of water per molecule of the drug Intol. Here, the crystals, liquid crystals, have about 320 molecules of water of hydration. A lot of hydrogen bonding going on there. Another more or less classical system for polymorphism is cholesterol acetate. High temperature phase, and I'd like to show you that. The liquid crystalline phase grows very rapidly, and we may see it here momentarily. It grows like a smoke across the field of view. This is just dirt in the molten cholesterol acetate, and there goes the liquid crystalline phase. The stable phase is already nucleating. You can see the liquid crystalline phase flowing. Unfortunately, this was too thick and I didn't supercool it quite enough, and I'm looking desperately for the colorful spherulites of the liquid crystalline phase and not finding it, of the solid phase I should have said. We'll do it over again. This is the liquid crystalline phase. Here you can see it still flowing. Here come the spherulites of the stable phase. And I'm trying to get over to the high first order colors. And of course you can't resist rotating the stage when you have pretty spherulites. Now I want to show you a very unusual phenomenon. I referred earlier to crystal strain, and this is really anisotropic within the crystal lattice. This is a compound developed as an explosive. It's a nitramine, bis-beta nitroethyl nitramine. And it grows with 4 different polymorphic forms, but what I'm going to show you is not polymorphism, but you will be amazed at what it does. Here the 2 crystal fronts have contacted and then proceeded to grow through each other. We'll watch a few more places. It's almost unbelievable. How can 2 phases, identical phases, grow into and through each other simultaneously? This can only be a result of internal lattice strain, and a good term for it is anisotropy of elasticity. The strain is actually oriented within the crystals in an anisotropic fashion. It means that, in a sense, the ends of these crystals are more stable than the sides of the crystals. There's quite a bit of general boundary migration, as I call it, in different parts of the field.